Hello friends. So in the last lecture we have seen about the cooling curves, and in this today's lecture, that is in the topic number 3, equilibrium diagram, we will just go with the further cooling curves. So in the last lecture we have just completed about the cooling curves of pure metal and the alloys. Now the remaining two cooling curves are there. So how that Gibbs phase rule has been implemented for the diagrams that we have seen in that particular lecture. So that Gibbs phase rule, the basic phenomena, the factors, that is P plus F is equal to C plus 1. So basically this is just a generalized mathematical equation for the Gibbs phase rule. And in this today's lecture, we are just going to complete this particular cooling curve for the remaining two phases of material. Now, what are these two phases? As far as that metals are concerned, what are the phases for pure metal that we have seen? In the pure metal, only one component is there, and for the alloys we are utilizing or using the two components, and that's why some sort of that in the phase diagrams, the F factor, that is the degree of freedom, that is the temperature, pressure or composition, so these factors maybe gets varied in step to step manner. Now in today's lecture we will just cover the third part of this particular cooling curve. Okay, so what is that? That is the cooling curves for eutectic binary alloy. So already we have seen the cooling curves for the binary alloy, but here we are just going to see the cooling curve for the eutectic binary alloy. So before going to start about this particular cooling curve, first you just try to understand what is the meaning of binary eutectic alloy. So the binary eutectic is the homogeneous mixture of two solids. So basically in the alloy we are using that particular alloy, it is just a mixture of two particular composition which are having the same phases. But here in the eutectic binary alloy, it is just a homogeneous mixture of two solids. Here we are getting the two separate solids. But in case of that alloy, only one particular solid phase we are occurring, even though the composition is somewhat different, but the solid phase is same. But here we are getting the two separate mixture of two separate solids which forms at a constant temperature during the cooling and melt at a constant temperature during the heating. So whatever may be the cooling curves, here we can be able to observe those particular tasks. So in case of binary alloy, this will be a liquid plus solid, only single solid it is there. This particular cooling curve, it is similar like a pure metal, but here the difference is that as compared to the pure metal, here we are getting the two different solid phases. Okay, so before going to start explaining this cooling curve, again I will repeat what is the binary eutectic alloy. So basically binary eutectic alloy is the homogeneous mixture of two solids which forms at a constant temperature during cooling and melt at a constant temperature during heating. So when that heating process goes on, means when we are increasing the temperature, whatever may be the its phase is there, that has been converted into the liquid. Okay, so it will be melts at a constant temperature. So when it will be converted into the liquid, we cannot be able to separate that two liquids. So it is just, we are saying it is just one single liquid. But when we are starting to cooling it, that is when the temperature is dropping, the two separate solids we are going to achieve, and that's why it is called as a binary eutectic alloy or eutectic binary alloy. So here S1, it is one solid, whatever will be the S1, it is indicated it is one solid, and S2 it is two solid. So when we are just cooling this, we are getting the two separate solids, that is S1 and S2. So this mixture appears in a definite morphology form and usually lamellar. So in certain cases, it may have a granular or some other type of morphology. Now, what is the eutectic temperature? You just try to understand the temperature at which this transformation occurs. Which transformation? That is, it may be a granular or some other type is the morphology. So when this transformation is going to occur, this particular temperature is called as a eutectic temperature, and it is the lowest temperature of the transformation in the system. Okay. So what is the eutectic temperature? I think you have just cleared this two things. Now, how the Gibbs phase rule we are going to apply on this particular phases that we are going to see. Now here we have just cleared what is the F, that will be the 2 for this particular phase. F it is 0, F it is the, again I will repeat, F is the degree of freedom. Okay, so here the degree of freedom is the 2. What is the degree of freedom? That is the relative term for the temperature as well as the composition. Basically here the temperature and composition, the degree of freedom is 0, so neither will be the temperature will be vary and composition will be vary. Here the degree of freedom is 1. Okay, so basically here we can be able to see the temperature is going to vary. So composition means when we are going to achieve these two separate terms, there is no any issue with the composition. So the temperature indicator on the y-axis, that is in the degree Celsius, this will be a time indicator on the x-axis. Okay, so now region wise how it is applied we are going to see. Now the eutectic alloy is the one that undergoes the eutectic reaction during the cooling. So when the cooling will be started, the liquid, when we are dropping the temperature, that is the constant temperature, when the temperature is going to be on drop, okay, or we can say that when the cooling will be started, so we are going to achieve the two different solids. So here we will say that is the solid 1 and solid 2. So that will be indicated over here as an S1 and S2. So thus the eutectic alloy when cooled form the two different solid phases. These are the two different solid phases when the cooling will be started. So that particular figure shows the cooling curves for the binary eutectic alloy. Now the binary eutectic alloy thus has the two elements which are completely soluble in a liquid state but entirely insoluble in the solid phase. So for the alloy, whatever maybe the solids are there, we are getting on one single solid state itself. But when the eutectic alloy it is there, when we are just heating it, okay, we are getting the single liquid, means we cannot be able to separate that liquid. That is called as a completely soluble in the liquid, means both the that particular solids are completely soluble in the liquid state. But when we are just cooling it, it is totally insoluble in the solid state. So we are just getting the two separate solids which are not soluble in the solid state. So this is just a meaning of eutectic binary alloy. Now in the region AB, the liquid state, the solidification start at B and continues until C. So AB is the liquid state. Okay, here again A, B, C and D. So at point A to B, the complete state is the liquid. At the B state, the solidification will be start till C state. Okay, so that's why it is just combination of liquid and solids. So two different kind of that solid state we are going to achieve, and after again the further cooling extended from C to D, we are getting the only solid state, but the two different solids we are achieved in this particular state. Okay. Now, how that Gibbs phase rule has been applied, that we will see in the region A to B. Okay, P plus F is equal to C plus 1. This is the Gibbs phase rule mathematical equation. So, T, that is the phase 1. So, I hope you understood what is that T1 why it has been taken, C is equal to 2 why that C2 has been taken. Okay, so I hope that you have just understood. Now here the P is equal to 1. Why that P is equal to 1? Because only the liquid is the state. Okay, and that's why here in the P we have taken only the liquid phase, and that's why this is the indicator of 1. Now why C, that is the C is equal to 2. Why it is true? Because here we have used the alloy. Alloy, it is the nothing but the binary. Okay, the two different materials are there, and that's why that C we have taken as an 2 over here. Okay, so in this equation C is equal to 2. Why it is 2? Because two different metals we are using, that's why it is the alloy. So the composition is that 2, and when we are just solving it, we are getting F is equal to 2 in this particular phase. Now what is this 2? That is the two variables, that is the temperature as well as composition, can be varied without affecting the liquid phase of the system. So how it is 2, that we are just seen over here. Now can you able to apply? This is for the region BC. Now for the region BC, B to C, P, three P's are there. That is the phases are 3. Why 3? Don't take as an only 2 phases, because solid phase we are just achieved in the 2 different parts, and that's why the total phases are 3 in this particular region. Okay, from B to C, the phases are 3, compositions are 2. Okay, so we have to find out the F. So here this again the pressure we are keeping the constant, that's why that Gibbs phase rule we have taken the 1 as a constant over here. So if the pressure is not constant, okay, we are not doing this procedure for the constant pressure, then this term will be 2. But lot many researchers, they have just keep the pressure as a constant, and that's why this one term will be there. So P plus F is equal to C plus 1. So phase is the 3, F is equal to this F that we have to find, and C compositions are 2 because the binary alloy, and that's why always C we have to take for the binary alloy 2. In the pure metal, this C we have taken as a 1, right? So in the last whatever lecture I have explained itself, for the pure metals this C will be 1. Why the phases are 3? Once again I will tell you, the phases are 3 because in this particular zone we are getting the 3 phases, that is the liquid plus 2 different solid phases, and that's why that phases are 3 over here. And when we are just solve, we are getting the degree of freedom is equal to 0. So the 0 means no variables amongst the temperature and pressure can be varied without changing the liquid plus solid phase of the system. If the temperature is increased, the metal goes into the liquid state, and if the temperature is lowered at this particular phase, it will be goes into the pure solid state. Okay. Now for the region CD, P plus F is equal to C plus 1. For the region CD, phases are 2. Now just don't be confused why the phases are 2. You may say that only sir solid phase it is there, but no. Two different solids we are achieving, and that's why we are taken the two different phases of the solid. So that's why P is equal to 2, C is equal to 2. Again, the composition, because the binary alloy. So always we have to take the C 2. Okay. So 2 plus F is equal to 2 plus 1. So F we are getting the 1. So this F is equal to 1 means that only one variable, that is the temperature, can be varied without changing the solid system. So here the temperature can be dropped. So this temperature changes may be there, but the solid system will not be changed. So the only degree of freedom is 1 for this particular zone, that is from C to D. Okay. So this is for the cooling curves and how the degree of freedom has been calculated for the cooling curve that I have explained. Now we will just go with our last cooling curve, that is the cooling curve for off-eutectic binary alloy. Now only the one word is added over here, that is the off-eutectic. Now what is this off-eutectic and how it is just differ from this previous system that we will see over here. Now what is the meaning of off-eutectic binary alloy, that you just understood this particular term? Eutectic transformation occurs for a definite composition called as a eutectic composition. Okay, if the composition of alloy differ from this, it is called as an off-eutectic alloy. What is the meaning of off-eutectic alloy? So the eutectic transformation occur for a definite composition. So composition will not be varied in that case, and it is called as an eutectic composition. But if the composition of the alloy differ from this, it's called as an off-eutectic alloy. So off-eutectic alloy are either hypoeutectic or hypereutectic type. So what is the meaning of hypoeutectic and hypereutectic? So hypoeutectic alloy have composition less than the eutectic composition, while hypereutectic alloy they have composition more than the eutectic composition. So the composition maybe gets varied. So before achieving in the previous diagram, here we can be able to see the liquid phase, suddenly the two solids separate out immediately because at a certain temperature. So the temperature will be the same, okay, just to form the two different solid state. So at a fixed temperature, at that particular temperature itself, suppose if it is 100 degrees Celsius. So at the 100 degrees Celsius, okay, we are just achieving these two different solids, okay. But here in the off eutectic alloy, here only initially we are getting the only one solid phase, okay. It may be a S1 or it may be a S2. So this is called an off eutectic, and this is because a certain composition in that particular material maybe have the different kind of the temperature, melting temperature. So that's why initially we are getting the different kind of that only one single solid, and once again when we are dropping that particular temperature, again the second solid phase will be immersed. So in this particular phase, you just understand both the solid state will not be achieved at the same time. So solid 1 or either it may be a solid 2, anything you can be able to take, it is initially appears, and at that time the second, whatever may be the second solid state, it will be there, it will not be appear at this particular temperature. But once again when you are going to drop the temperature, the second solid state will be appear, okay. So this will be the basic phenomena of eutectic binary alloy. So I hope you have just understood this particular term, that is what is the S1 and S2. So L plus S1 plus S2. Okay, so this will be the cooling curve for this. Now here we can be able to, this zones will be divided A to B, B to C, C to D, D to E. So in this manner, this cooling curve has been differentiated. Now in this cooling curve, just see what is in the A to B phase. Now eutectic reaction occurs for a definite composition and definite temperature, okay, but in the composition of alloy differs from the eutectic composition, it is referred as an off eutectic alloy. Now off eutectic alloy with a composition less than the eutectic composition are called as a hypoeutectic alloy, and those with a composition more than the eutectic composition are called as a hypereutectic alloy. Now during the cooling of eutectic alloy, either of two solids separates out earlier depending on whether the alloy is hypo or hypereutectic alloy. So it depends on this hypo or hyper, this particular two terms will be differ. The pre-separated solid referred as in a pro-eutectic phase. Now figure shows a typical cooling curve for the off-eutectic binary alloy. This particular region A to B represent the liquid state. The solid state start at a B. Region B to C represent the solidification either or in the sense any one solid. Then the region CD represents the solidification of both, that is both the solid state, and the region D represents the solid state of entire system. So that is A to B, B to C, C to D, and D to E. Okay. Now how it is implemented, the Gibbs phase rule. Now P plus F is equal to C plus 1 phase, that is only one liquid phase it is there, so that's why it is taken as 1. Again it is the binary alloy, so C will be 2 for this particular region, okay. So here that phase is only the liquid phase, and binary alloy we have taken, and that's why that C is 2. So we are getting F is equal to 2, that is meaning of two variable temperature and composition can be varied without affecting the liquid phase of the system. So two variables in the sense temperature as well as the composition. Now in the region BC, in this particular region, it is either started the solidification of any one, and that's why the P is equal to 2 in this case. The phases are 2. Phases are why the phases are 2? Liquid plus only one solid we are getting. So it either may be a S1 or S2. That's why it is written in the bracket over here. It will be a L plus S1 or L plus S2. Depends on the melting temperature of that particular solid. And that's why the P taken over here in this particular region, P is equal to 2. That C is equal to 2 because binary alloy it is there, and that's why the degree of freedom is equal to 1. That is, the meaning is that only one variable, that is temperature, can be varied without the solid state. So composition will not be varied. Now similarly for region C to D, now region CD, just observe in the region CD, here we are getting the 3 phases liquid plus 2 solid phases, and that's why P is equal to 3 over here, C is equal to 2 because of the binary alloy, and when we are just calculated this particular term, we are getting F is equal to 0. That is, meaning is that there is no any kind of that degree of freedom in this particular zone. And for the region DE, the phases are 2, that is 2 different solid states are there, composition is 2. So once again, we will just go with this region DE. The phases are 2, that is S1 and S2. The liquid phase will not be there, but in the solid phase, the 2 different solids are there, that is S1 and S2, because the 2 different metals are there, that is S1 and S2, and that's why this P is equal to 2, C is equal to 2, because again the binary alloy is there, and when we are calculating this, we are just getting F is equal to 1. That is, the meaning is that F is equal to 1 means that only one variable, that is the temperature, can be varied without changing the solid state of the system. So these are the 4 cooling curves what we have seen up till now. I hope you have just understood how that Gibbs phase rule is implemented according to the phase to phase in the cooling curves. So in the next lecture, we will just move ahead with the further part. So thank you very much for the patience listening, and then in the next part we will just start with some sort of that equilibrium diagrams, which is very much important as far as that material science is concerned, as far as that mechanical engineering is concerned. So thank you very much.